and I am a meteorologist at Met Service. I have been forecasting for about 5 years now. 3 of those have been as an aviation forecaster, so TAFs, graphs, all that stuff, and the other 2 have been as a public forecaster, and that's been writing the worded forecasts that you would see on the website or the app. And so today I'm going to talk about the weather models that we use at Met Service and the value that us as meteorologists can add to them. So a brief outline, I'm going to talk about the sort of 3 main types of models that we use, our globals, our internal WRFs, which Chris has already mentioned, as well as the ensembles. I'm then going to take a quick look at models versus reality, particularly with respect to terrain. What it can look like when models diverge and what we do as meteorologists when they do, and a brief touch on verifications. Are we really as good as we claim to be? So what is it that we do? We write forecasts, and that forecast is sort of made with 3 main components. That is our observations, our met knowledge as forecasters, and models. So our observations are things like the radar network, satellite imagery, our weather station network, webcams, also things like ATISs and AMDARs are really valuable to us. When I talk about met knowledge, I'm talking about the training that we do to become a meteorologist, learning how systems work and how the atmosphere moves, becoming familiar with our aerodromes that we write forecasts for and the surrounding terrain, and how that affects what happens at the aerodrome. So whether or not cloud will form in certain wind directions and what wind directions a certain place can get. So for example, Milford is a big one where they only really get a northwesterly and a southeasterly. So then the last bit is the models, which are very important, obviously, to writing a forecast. That's things like rain output, wind, swell, as well as looking at what's happening through the atmosphere. So we take these 3 components and we write a forecast, and today I'm going to focus on the models. So at Met Service, we use 3 different global weather models. And when I talk about these global weather models, I'm talking about what we call a deterministic. So this model is a single data sample of the atmosphere run through a model. They run almost across the whole planet about every 6 to 12 hours out to a week, but that depends on the model. And they take a long time to run, about 6 hours. So some of the world's largest supercomputers are running weather models. So the 3 that we use at Met Service are the EC, which is quite a popular one that people might know of, the UK, and the GFS. The EC is run out of Europe, and you can see there's a supercomputer on the right there. The UK is run by the UK Met Office, and the GFS is the American model. These models are usually dependent on latitude, so the horizontal resolution will change depending where in the world you are looking at it from. For the likes of New Zealand, the EC has about a 9-kilometre horizontal resolution. The UK is slightly coarser at 16, and the GFS coarser again at 22. What's also important to us is the number of vertical levels that they model for, because as we know as aviators, what is happening through that atmosphere is incredibly important. Share, cat, all that sort of stuff. So as well as the horizontal resolution being important, the vertical levels are also important. So the sort of physics that's used to describe that atmosphere in each of these models is different, and therefore they often produce different solutions or different outputs. Some do better than others in certain situations, and that's something that we learn as forecasters on the bench. We see like repeating patterns in models, and we can use that to determine whether or not we want to follow that model for the day. So it's our job as a meteorologist to evaluate the model, see which one's doing best today, and therefore that model might be doing best in the future. but we also have the ability to change the forecast as we see the models change and differ. So here's an example of what it might look like when we're viewing some guidance for our global models. We have the GFS, our American model here, our UK in the middle, and our EC to the right. What we're looking at is a 6-hourly rainfall accumulation up to this time, and our wind barbs are for at 850 hectopascals, so not at the surface. So this is a really nice and simple way to compare what our 3 main global models are doing for the same situation. So in this example, we have a low pressure system to the northeast and a frontal system moving on to Fiordland towards the southwest of the country. Some subtle differences in between these models. We can see that with this frontal feature, the EC has it much further to the west, whereas the UK and the GFS have it slightly further onto Fiordland. So, for example, we've got the EC bringing heavy falls through Fiordland, whereas the EC not so much. In comparison, though, the EC has a lot of light, sort of isolated precipitation up through Westland and Buller, and these other 2 models, our UK and the GFS, don't seem to be picking that up. This is quite common with regards to the EC being a higher horizontal resolution. It often has a tendency to forecast more of these sort of light isolated showers. But so these are the 3 main models we use, and we can have a quick side-by-side comparison of them when we're forecasting. The other thing that we like to do is compare the model against itself in terms of consecutive new model runs. So for each 3 of these images, we're looking at our UK model, and they are each for the same time, but our prognosis time, so how far away this image is getting shorter and shorter. So if we're heading right, each picture is a new model run. And we can say same situation, low to the northeast, a front moving into Fiordland. Once we get to the far right, we can see that there's been a change in the way that this model is initializing this low or creating this low. And that is in turn spreading this blue stuff over parts of the North Island, which it hadn't been before. And what we're seeing there is relative humidity or cloud. Another example here is this frontal feature over the south of the South Island. In this first panel, we can see there's quite a lot of clouds spreading eastwards over this sort of like Fiordland ranges. Whereas in the other 2 models, we're not seeing that as much. And that's probably due to the formation of this low pressure system to the south of the country, which is helping pull back some of that cloud over the east of the South Island. So it's really great that we can do this. So we can say, is the model consistent with itself? Is it telling the same story through time? Models have a tendency to flip-flop. For example, you know, I don't have cloud here and now I do. And that's where we come in, and we can provide consistency. So if we can see that the model has a tendency to do something and it jumps, we might not jump with it, and we'll watch and, you know, watch the system progress, etc. Cool. The next thing I wanted to mention briefly was Windy. Windy is fantastic. It's visually very easy to look at. When you're on Windy, down in the bottom right hand corner, you have the ability to choose the model that you want. There is the EC model down here, as well as the GFS, which are the 2 that we use at Met Service, the GFS being a coarser resolution than the EC. There is also the Access and the Icon model down here. We don't use these at Met Service, but I believe the Access is a bomb model, and Icon is from the German weather service. It's important to bear in mind that this is purely model data. It's not edited in any way. For the likes of the EC model, new data is only every 3 hours. So although you have the ability to go through time hourly, the data is not updating. And you can't compare models side by side, nor can you compare run after run. But yeah, I just thought I'd mention that there is a little eye down there that allows you to read a little bit more about each of those models if you're using it. So those are the global models. At Met Service, we also run our own models. It's a limited area model and we call it a WARF. So what we do is we take those 3 global models and we use their conditions to run smaller, finer resolution models over the country. And so those get run at 8 kilometres and 4 kilometres. So compared to the global models, the horizontal resolution is much finer. These run twice a day, up to 72 hours, with output produced every hour. And so by that I mean these graphical outputs of the data is every hour, whereas when we're looking at the global models, that's every 3 hours and tends to every 6 hours the further out you look. So we can look at the data every hour, which is nice. We're also running even finer, 1.5 over the likes of Auckland, Marlborough and Banks Peninsula, and that's what we're seeing in this image on the right is a 1.5 kilometre model. Obviously, the higher the resolution, the easier it is for the model to pick up smaller scale features. And so that's things like isolated showers. Thunderstorms is another good small scale feature that finer resolution models are good at picking up. Small wind eddies, etc. So higher resolution, higher detail. At Met Service, we actually have a forecast research and development team that works on the WARF models and are continuously improving them for us. So we had Chris talk earlier. So my job as a meteorologist is to look at the models, understand them and write a forecast, whereas we have the research and development team that knows the intricacies of, the equations they use and how the atmosphere works within the model and is continuously improving them. Here's an example of our WARF models. At the top, we have our 8 kilometre resolution, and then at the bottom, we have our 4 kilometre. You'll see you've got the names of the global models at the end. So this is the 8 kilometre GFS or NCEP. So this is run off the global parent model, and again, the same, but for a 4 kilometre. Looking at these images, what's immediately obvious to me is the way that the models are handling these showers to the northeast of the country. So you'll see in the 4 kilometres compared to the 8 kilometres, there's a lot more finer shower activity happening to the northeast of the country. And similarly down for the south of the South Island, there's a lot more well-resolved shower activity happening compared to the 8 kilometres. So in general, higher resolution, we get slightly more detail. That's not always a good thing, but in general it is. And the other sorts of models that we use, which again, Chris also mentioned, is ensemble models. And so that's when we look at multiple data sets. So with regards to our global deterministic models, they are taking the best guess of the atmosphere and running with it. Our ensembles slightly adjust the best guess of the atmosphere and run with that, which gives us an idea of spread or uncertainty. So due to computer limiting powers, basically the atmosphere being almost impossible to perfectly model, every forecast is uncertain. That's exactly what it is. It's a forecast. So ensembles will start from a slightly different state and run with it. And the spread that we see in the ensemble members gives us an idea of the uncertainty on that day. So if we were running it during like a high pressure situation, there's probably not going to be a lot of spread because this high pressure system's not moving, etc. But for the likes of, say, a tropical cyclone, which is a much more volatile system, you're going to have a lot more spread with your ensemble members. And so we use this to help us gauge uncertainty. One example of ensembles that most people will have seen is your tropical cyclone plots. So this example was actually from Ian, which passed over Florida a few months back and actually caused quite a lot of damage, unfortunately. But we can see each of these lines represents a single member of the ensemble being run at a slightly different state. And this gives us an idea of spread because we can't predict the atmosphere perfectly. Having a range of what the atmosphere might be doing and how that changes with time is really important. It also gives us the ability to forecast things like intensity, wind speed, pressure, etc. So those are the main models that we use, and they are pretty good, but they're not perfect, and they won't always be, and that's where us as a meteorologist comes in. So this graph is from the EC website, the EC model, and what it's looking at is how good we are at forecasting what is, or I should say modeling, sorry, geopotential height throughout the years. The color codes refer to the days out of forecasting. So the blue is 3 days out, red is 5, green is 7, and yellow is 10. So throughout the years, we are getting better models. The models are getting better with time, but they're not perfect. What I also think is interesting with this image is the thick line represents forecasting what we call geopotential height in the northern hemisphere, and this lighter line is the southern hemisphere. And you'll notice that for each of these plots, the southern hemisphere forecasting always does worse in general than the northern hemisphere. Our three main global models, Europe, UK, and America, are all Northern Hemisphere models. And there's a lot more data available in the Northern Hemisphere. So we have more flights, more ship routes, etc., that gather data and are able to feed that into the models. So in general, the models perform ever so slightly worse across the Southern Hemisphere, but it is getting better to the point where they're almost the same. So going back to our WRFs, or all the models really, they have a horizontal resolution, and that means the terrain of the country sort of gets stretched out over these horizontal grids. And that is very obvious for our regions with lots of mountains and valleys, which is actually quite a large portion of the country. And so I've got a graphic here of what the terrain looks like across the country for the 8 kilometre and the 4 kilometre WRF. And so you'll see the 8 kilometre is coarser. It doesn't get the details as well as the 4 kilometre. So for the likes of like Ruapehu and Mount Taranaki, you can see that the heights are higher and better resolved in the 4 kilometre than the 8 kilometre. And yes, the 4 kilometre is better, but it's not perfect. So for some examples, Queenstown Airport sits at about 356 metres above mean sea level. In the 4 kilometre WRF, it believes that the height of Queenstown is actually 668. Some more examples, Milford sits at 3 metres, but the WRF thinks it's almost at 760. And similarly for Mount Cook. And we will all know as aviators that the terrain plays an incredibly important part in forecasting. Winds channeling through valleys, hills blocking precipitation. So If the models don't have a sound understanding of where these airports lie, then they're also not going to have a sound understanding of what the weather is doing at the airport. And so that's where we come in, and we use our knowledge, what we learn on the bench, what we see regularly, to improve what the model, gives us as an initial best guess. So we have what we call wind roses, sorry. And they show us what wind directions places get and how strong they get them. So for example, down here in Pusiga Point, the northerlies come through much stronger with these reds than the southeasterlies. Another one is Milford. Obviously, the model thinks it's a lot higher than it is. And so often we'll see the model forecasting like easterlies coming through Milford, but we know that because of the terrain, they really only get a northwesterly and a southwesterly. And so we can add that value to the forecast. We also have fog flowcharts and general weather flowcharts for some of our aerodromes. So depending on the wind flow at certain places, we might know that they will or will not fog or will not get low cloud. So there are situations where there's like low cloud coming in through Christchurch in the models, but you know that there's a really strong northwesterly aloft, and you can see that in the observations, and you know that low cloud and fog doesn't form in those conditions. So you can add value and say, actually, I don't think there's going to be low cloud. We also have issues where the models, what we call diverge, they go their separate ways between themselves and between reality. And so in this example, we have our two 8-kilometer wharfs and a 4-kilometer wharf. And you can immediately see there's a very different wind strength across the Lower South Island in this 4-kilometer compared to the 8-kilometer. And you look at this and you think, who's doing the best? So that's where we come in, where we say which model is doing the best now. That model potentially may be doing the best in the future, so we'll use that model, and then we watch how things progress. We watch the OBS. A really common one is a southerly buster through the east of the South Island, where the models might be forecasting a 15 gust 25, and you see that come through, say, Oamaru as like a 25 gust 35. The models are not with reality, they've diverged, and then you can go through and amend your forecast for further up the coast for stronger winds. And so in this situation, what happened? It's hard to tell. We've got 45 knots coming through Stewart, and so we're comparing what's actually happening to the models. And some of the models do have some strong winds, but there's a very light northwesterly coming through Pusiga, and the models were almost wanting like a storm through there. Another example is through Dunedin, where it's got quite a good northerly gradient, which these guys may have been a bit more onto rather than the 4K, but then again, they didn't really capture what was going to happen across the south coast. So sometimes we do end up taking bits from certain models or adjusting it as we see fit. Another good example was tropical cyclone Philly back in April. The media made a pretty big wahoo about this guy as it was approaching the country. 3 days out, this is what our deterministic global models looked like. And what we're seeing here is over 100 millimeters of rain within a 24-hour period, which is a lot over the North Island. The low system of Philly is also placed differently, which has a massive effects on what the winds are going to do. So, are we forecasting a really strong southwesterly through Auckland, or are we forecasting a strong southeasterly? Because that difference in wind direction does matter to them. So seeing this is quite scary, but what happened ended up being not a whole lot. So this is the radar through the day. A lot of this precipitation we're seeing in the radar is quite light. So the deterministic models really didn't have a proper grasp on what Philly was expected to do as it headed towards the country. When forecasting something like Philly, a tropical cyclone, that's when we refer back to ensembles rather than the deterministics in the images I just showed you. So this is what our tropical cyclone forecaster issued with time. And we're tracking the low position of Philly, and the cone is not the cone of effect, but rather the cone of uncertainty of the low position. But you can see that, far out, we weren't forecasting the system to track right over the country and bring incredibly awful weather. We knew what happened. No, we knew how hard these systems would forecast. We took, a bit of caution. We took the ensembles and we forecasted it. And you can see with time, we treated the system more and more to the east of the country, which is sort of what the ensembles eventually wanted. So when thinking about verifications, are we really that good? In general, yeah, it depends on the situation. In general, we tend to do better during high impactful events. So during the Nelson Red warning in August, awful flooding through Nelson. During that event, the WRF models were forecasting about 200 to 300 millimeters of rain into the ranges of Nelson. What we were communicating with Nelson Council was more like 350 to 500 for those Nelson ranges. And after the event, through our AWS observations, they recorded about 400 to 500 in those ranges during the period of the event. So this is a case where we were pretty onto it and had seen the sort of river of rain system before, knew the models had a tendency to under forecast in this situation and therefore increased our numbers. We're not always better. So this is verifications for our inshore marine forecast. So this is for wind. And this is our forecast percentage score. So we want to be higher. And then this is a function of time. So the further out the forecast is. For the likes of Hauraki, in general, our models, which is the blue, black, and green, do better than us as a manual forecaster in red. However, for the Wellington inshore marine area, we tend to do a lot better than the models, particularly with longer lead times. And for Christchurch, we're about the same. So we can perform in general to the same precision that the models come. So we're not always better, but we're pretty good. And that is sort of where I'm finishing up.